Hey guys, today we're looking at 7.7's note, which is all about factoring with our special products. So if you remember back in 7.3, we went through and looked at some special shortcuts for how we could multiply two binomials together, two parentheses together, without having to FOIL or box multiply or any of those other methods that we did. And if you remember, these were those shortcuts. So taking a look over here in box number 1, we had our sum and difference formula, which we're going to call the difference of two squares. I probably started using that already in 7.3. That's where if we have two things that are being multiplied together that are the same numbers, the same terms, but one of the parentheses has a plus in between and one of the parentheses has a minus in between, that always multiplied out into that first thing squared minus that second thing squared. So that's why we call it a sum and difference formula back in 7.3, and why we'll focus on calling it the difference of two squares. Because when we see it already simplified out, already multiplied together, it literally is a perfect square minus a perfect square. It's the difference of two squares. Our other one was our perfect square trinomial. So in that one, we have two different versions of it, depending on whether that parentheses squared is a plus b, or a sum, or a difference. The pattern looks very similar. Our answer in standard form was always a squared plus or minus, depending on the original one, plus or minus 2ab times b squared. And this one, I would say, again, like we talked about back in 7.3, I would say this factoring shortcut far less useful and beneficial or utilized than the difference of two squares. Because if you notice this perfect square trinomial, it looks pretty similar to the other factoring stuff that we've done, where we've got, a squared plus something a plus something squared, whatever it is in this case. You could use just regular two parenthesis factoring or Xbox factoring if you had to on the perfect square trinomial ones. But our difference of two squares is two terms, so it's just a binomial. And we're trying to factor those. So those are going to be a little bit more unique, a little more obvious to when we're going to use them, and a little bit more applicable for us when we actually go to start factoring. All right, so let's go ahead and jump into our other boxes and actually put these into use. And we can take a look at what it looks like working backwards. Because now, obviously, we're wanting to use these same patterns, but working backwards so that we can take something that's already been multiplied together and factor it out. So when we're looking for these, the big thing is going to be picking out when our first and last terms are perfect squares. Because if you look at both of our patterns, our difference of two squares, obviously, those are both perfect squares. But even if you look at our perfect square trinomials, my first term and my last term, those are also both perfect squares. So this section is basically going to be working on identifying when we have perfect squares as our first and last numbers, and whether or not the rest of the pattern fits with what I'm given. Because, like I told you guys last week, when we get to the test, it's not going to say factor using this method, factor using, two parentheses factoring, factor using Xbox factoring. It's just going to be a section that just says factor the polynomial completely. And you're going to have to just know which ones you can and can't use. And we'll work on developing some of those skills and identifying when you can use a certain method or not, to make it a little bit easier for you, because obviously there's some methods that work all the time, like Xbox factoring will always work, but that was also a lot of work. So we want to try and find the best one for our given problem. So taking a look at box number 2 here, we're working on, these are going to be examples of factoring using the difference of two squares. And in order to be able to factor using the difference of two squares, we first have to make sure that we do have a perfect square minus a perfect square. So it might be beneficial for you to write out what the terms are if it was a perfect square, because what we should be able to do, no matter how pretty or ugly the term is, we should be able to write this as something squared minus another thing squared. Right? That is the definition of what a perfect square, or a difference of two squares is. So in here, we could say, all right, well, this first thing is obviously x, because if I square x, I would get x squared. And here, if I squared 5, I would get 25. So pretty easy to see that this is a perfect difference of two squares. Once I know that, my x is my a value, my b is 5. And if you look back over here at this pattern, it factors out into a plus b times a minus b. So what this would factor out into would be my first parenthesis, x plus 5, and my second parenthesis, x minus 5. And that would be factored completely. which also makes sense because here we don't have a middle term, which means the coefficient on that x term would be 0. We're trying to figure out what two numbers multiply together to give me negative 25, but adds up to 0, which would have to be positive 5 and negative 5. Those add up to 0, but multiply together to give me negative 25. So that's, I think, the most likely for us to see a difference of two squares factoring pattern, something like that, where my first term is just a variable squared, my second term is just a perfect square. There are uglier ones, like here, number 2, we've got 9z squared minus 16. And again, my first thing is going to be to try and figure out if there's something I can write so that it's something squared minus something squared. Now, with my 9z squared, I recognize the z, right? I'm definitely going to have a z inside here. But I have to also make sure that that coefficient is also a perfect square. So in this case, 3 squared is 9, z squared is z squared is z squared. So if I squared 3z, I would get 9z squared. So 3z is that first term. And then over here, 16, we know that that's 4 squared. So that means my a value is 3z, and my b value is 4, which means when I write this all factored out, I end up with 3z plus 4 times 3z minus 4. And that is factored completely, because 3z is the thing that you would need to square to get 9z squared. 4 is what you'd need to square to get 16. So there it is. All right, those ones are the ones that, again, I use all the time. If you, again, like I talked about in 7.3, if you're only going to walk away with one of these skills, one of these shortcuts, it would be your difference of two squares, your sum and difference formula. These are the ones that we utilize all the time. Everything else, these last two boxes, if you could recognize them, it is a shortcut. It'll take you, less time. You won't have to think about, Xbox factoring or two parentheses factoring. You just recognize, oh, hey, my first term is squared, my second term is squared, my middle term is 2 times those things. So then it fits with my pattern, and I can go right to what the answer is. But you also could, like looking at number 3 here, we could just factor that using my regular two parentheses factoring. But just for the sake of some practice, let's take a look at this as if we're going to use our perfect square trinomial shortcut. So just as a quick reminder, our perfect square trinomial, we have a plus b parentheses squared, so something times itself. And my pattern is my first term is a perfect square, my last term is a perfect square, and then my middle term is 2 times each of those two things. So what that looks like, the pattern I'm trying to get this to fit in is that this thing squared plus 2 times my first parenthesis times my second parenthesis plus my last thing squared. Right, where maybe I'll do this in different colors. So this is the same here, and green here. So I always start on the ends, right? My first term and my last term. Here again, it's easy. Y squared is y squared. 3 squared is 9. So that means if this pattern holds true, my middle term should be 2 times y times 3, which if you multiply those out, you do end up with 6y. So this pattern does fit. That tells me my a is y, my b is 3. So this factors out into y plus 3 parentheses squared. Which, again, if we look at it in terms of regular two parentheses factoring, that would be y plus 3 times y plus 3. 3 and 3 does add up to 6, but multiplies to get 9. So it still does fit using that other method that we looked at. And I would not use this method on that particular problem. If I was just given that problem, I would just look at it and use my regular two parentheses factoring. 3 and 3 multiplies to get 9, but adds up to positive 6. Where it is a little bit more useful, and again, if you recognize it as a perfect square trinomial, something like number 4, where you've got a lead coefficient on that squared term, where you would have to use Xbox factoring. If you could recognize it and not Xbox factor, I think a lot of us would be a lot happier to not have to Xbox factor a whole lot. So again, I'm looking at, maybe I'll use black here. So I'm looking at my first term being a perfect square plus 2 times my first term times my last term plus my last term squared. So if this does fit, 169, it's not a common one, but 169 is 13 squared. Again, use your calculator to check it to see if it's a perfect square or not. I'm going to have to move this over here a little bit to make sure it all fits. And then for my first term, well, if that's 13, that also has to be 13. Because remember, 2ab is my middle term. My first term for m squared, obviously, m squared is m squared. And then 2 squared is 4. So 2m should be that a term, which if I multiply all these together, 2 times 2m times 13, I do end up with 52m for that middle term. So my pattern does fit. So the way that that would factor out then, it's if this is my a value and this is my b value, right? Because this is 2ab plus for my formula, 2m plus 13 parenthesis squared. Okay, that's my difference two, or my perfect square trinomial when it's a plus, when it's a positive in between. Now, box 4 is pretty similar. It's perfect square trinomial still, but now it's subtraction in between. The only thing that changes is that minus 2ab means that it's a minus b parentheses squared. I'm still doing the same pattern. I'm still looking for my first term squared plus 2ab plus b squared. You don't necessarily have to follow the same format, but it fits for me if I think that if I recognize that first and last term as being perfect squares, where b squared is b, and then 4 squared, nope, why did I write, oh yeah, b. A little confusing because my b's are different than my b term in the formula. But either way, we end up with b squared plus 2 times, oh sorry, minus. So the only difference here is that because it was minus 2ab in the middle, minus my 8b, my answer ends up being b minus 4 parentheses squared instead of b plus 4 parentheses squared. Now, once again, I'll reiterate this. If I saw this problem, I would not use this factoring shortcut. 2 parentheses factoring to me is much quicker, so go ahead and use that. You would try and figure out what multiplies together to give me positive 16, but adds up to negative 8. Negative 4 and negative 4, and you'd get the same solution. But if you saw something like number 6 and you didn't want to Xbox factor, and maybe you see, oh, hey, look, 4v squared, that's a perfect square. 9 is a perfect square. Let's check to make sure that this pattern holds. 2ab plus b squared, where, oh yeah, 2v is 4v squared, and then 3 is 9 when you square it. So, and that middle term does fit. Negative 2 times 2 is negative 4. Negative 4 times 3 is negative 12. And I still have that v, so negative 12v is my middle term. So that means when this factors out, my first term is 2v minus 3 parentheses squared. There we go. So that is factoring with our special our special products, our shortcuts. One more time, I'll say it again. If you're only going to take one thing away from it, box 2, difference 2 squares. It is very, very useful for us. It is something that we commonly see. It is something that I will commonly throw at you. And there's no other, I mean, kind of. I mean, you can technically Xbox factor and you can technically, 2 parentheses factor, but it's a little more difficult because you don't have that middle term. It's only the first term and the last term that we see. And that is much quicker. If you can recognize that, especially because the only time we can factor anything when it's only 2 terms that we're factoring is with a GCF or and the difference 2 squares. That's it. So definitely to make sure you guys understand and can do box 2 with our difference 2 squares. If you can recognize boxes 3 and 4, that's awesome. It'll help you. It'll be a little bit quicker for a lot of the cases, especially when there's a coefficient attached to that lead term. So you don't have to Xbox factor, but it can be done with other methods. All right, so homework for tonight, page 401, 4 through 40, every other even. Be aware or be kind of careful, 28 and 32, both of those are asking you to solve the equation with these new methods. So give it a shot. We'll talk through those if we need to tomorrow at the beginning of class to kind of work through those before we see some more factor and solve problems from this section. But everything else is just regular factoring stuff. You should be able to handle the rest of it without much difficulty. If you get thrown off by 28 and 32 because they're solving and we didn't do any solving problems on the notes here, that's okay. Just circle them, and then when I ask if there's any questions at the beginning of class tomorrow, then obviously ask those ones. But otherwise, that's all I got for you. So have a fantastic day. If you have any questions, concerns, thoughts, ideas, hopes, or dreams, make sure as always you're reaching out and letting me know. And we'll see you tomorrow.